Okay, so as we talk about differentials, a good way to start that out is by thinking about or remembering the case when we just were dealing with one variable. Okay, so when we had a function of one variable that was differentiable, we defined the differential dx to be an independent variable. So that means dx can be any number you want, any value you choose. And based on that, dy is now going to be dependent and depends on your choice of dx, and it depends on that derivative at the point x. Okay? So in actuality, believe it or not, dy depends on two variables. So dy is a function of x and your choice for dx. Right, so typically this is really small, and x is just a location. Okay. And then this was the picture that this is a geometric description of what was going on. So remember before with linear approximations, we're looking at increments. So the increment in x, which is delta x, is this distance from a to a plus delta x, right? And now we've got a distance between f of a. Let me do it here. Let's pick a different color. So f of a and f of a plus delta x are here. And so the increment in y is the distance between is f of a plus delta x minus f of a. So that's that distance. Okay. So increments go with linear approximations. Differentials are slightly different. Now here's the deal. For a differential, dx, you choose dx. Okay. So in the picture, dx is the same as your increment in x. So dx is some small little distance, and dy is the difference between, so let's use a different color here. dy, which is your differential in y, is the difference between the linear approximation using a plus delta x. So this is the linear approximation with a plus delta x, right? Versus this is going to be the same thing as your linear approximation at a. And so this distance here, this is your dy, your differential. So your differential is using the linearization, okay? And the linearization is using the derivative. So that's the connection in one dimension. And we have something very similar situation for two variables. So when you've got two dimensions for your input. So now dx and dy are independent variables, and dz depends on dx and dy. So here's the formula that we'll have, the formula you want to capture is right here. Okay, so remember, this is an input, this is an input. These are typically small. And we're assuming that our function is differentiable. We're assuming that f is differentiable. So these derivatives, fx and fy, are definitely exist. And we're able to approximate f very well with the linear approximation. Okay. Now this is called the total differential because it takes into account the x direction and the y direction. Okay? So what I want to do is I want to show a picture. This is the 3D version of the 2D picture that we had before. So now delta x and dx are in this direction, and your delta y and dy are in this direction. Now, with linearization, your increment is the difference between the value of the function, here, and the what are we saying? Not the value of the function here. Just kidding. The what is it? It is going to be the difference between the actual and, let me see. Let's go back. So our delta f or delta z is equal to f of a plus delta x comma b plus delta y minus f of ab. Okay, so this is the difference between the height here and this height here of the f of ab. So now if all of this is f of ab and all of this is f of a plus delta x comma b plus delta y, then this increment is going to be this distance from here to here. Okay. All right. So that's the increment. And now let's compare that with the differential. So dz now is going to be your fx at the point AB times your delta x, your dx, sorry, plus fy at the point AB times dy. And this ends up being the linearization of a plus delta x, comma, b plus delta y. Yes, this ends up being that linearization, okay? So that dz is represented in the graph by the difference between your f of ab. So this is this linearization, sorry, minus the actual value f of ab. So that's what this is. So this height from here to here is this first part here, right? And this height from here to here is the height of f of ab. And so the remaining height is your dz. Okay? And so the linearization, again, that we're using is that tangent plane. Okay, so just to recap, your differential is based on your linearization. And your linearization is based on your increment. Okay, so let's do an example here. So if z is equal to x squared plus 3xy minus y squared, find the differential. Okay, so let's find that differential. Now we have the formula. The formula is going to be dz equals, fx xy times dx plus fy xy times dy. Okay, so we need the partial with respect to x, and that is going to be 2x plus 3y. So we should have 2x plus 3y times dx plus, now the partial with respect to y is going to be, that's going to be nothing. With respect to y, we'll get 3x minus 2y plus 3x minus 2y dy. All of that is equal to dz. Okay, now let's answer part B. If x changes from 2 to 2.5 and y changes from 3 to 2.96, compare the increment in z with the differential. Okay, so now here's the deal. Let's first, since we already have the formula for the differential, let's work with that first. Okay, so we know that dz, so we've got our formula for dz, and it is equal to, what do we have? 2x plus 3y dx plus 3x minus 2y times dy. Now, in terms of differentials, if you tell me the x changes from 2 to 2.05, that means that dx is equal to 0.05. Okay? And y changes from 3 to 2.96, then that means overall we had a decrease. So dy is going to be negative 0.04, right? Because that's going to be 2.96 minus 3. Does that make sense? Okay, so here in my formula, I've got 2x plus 3y times my dx is going to be 0.05, and my 3x minus 2y, my dy is going to be negative 0.04. I'm not done yet. I need to figure out what's x and what's y. Well, it says x changes from 2, so our starting point is x is 2 and y is 3. So let's plug in that x is going to be 2 and y is going to be 3. 2 and y is going to be 3. All right. So now what do we get? That'll be 4 plus 9 times 0.05 plus, that'll be 6 minus 6 times negative 0.04. So that'll be 13 times 0.05. So we just have 0.65. Because that's just going to be 0. Okay, so our differential is 0.65. Okay. Now, let us determine the increment. So, the increment in z is going to be the difference between f of 2.05 comma 2.96 with the starting point, which was 2 comma 3. Okay, so now what is f of 2.05? What's our formula for f? F is x squared plus 3xy minus y squared. So I need this squared plus 3 times 2.05 times 2.96 minus 2.96 squared. Okay, all of that minus 2 squared plus 3 times 2 times 3 minus 3 squared. Okay, and what do I get? I'm going to plug this into my calculator. Okay, and then minus 4 minus, what is that, 9? 18? 18 plus 9. Okay, and I got 0.6449. Okay, so our increment in Z is 0.6449. They're pretty close. So DZ is pretty close to the increment, but it was a lot easier to compute the differential. Right? Okay. And let's look at one more example here of using differentials. Now the base, radius, and height of a right circular cone are measured as 10 centimeters and 25 centimeters respectively, with a possible error in measurement of as much as 0.1 centimeters in each. Okay, so now right circular cone, what does that look like? That looks something like, right, so the base is a circle, right circular cone. And basically, you know, if you use a ruler, it's not exact, it's not precise, so you have a margin of error. And it's saying that the base radius, so this radius here, so this radius is measured to be 10. So the radius is equal to 10 plus or minus 0.1 centimeters, right? And the height, so the height, which would be from here to here, was measured to be 25. So it's 25 plus or minus 0.1 centimeters. Okay. And we're supposed to use differentials to estimate the maximum error in the calculated volume of the cone. Okay, so we know that formula for volume for a cone with base R and height H is going to be pi times R squared times the height over 3. So 1/3 pi times R squared times height. So this is our formula. Okay, so that means that volume depends on the radius and the height. Sorry. We want to use differentials. So the differential is going to be equal to, now we need the partial with respect to R times the differential in R plus the partial with respect to height of V times DH. Okay. Now, what is our partial with respect to radius? Okay, so if we say V is equal to, now if we write it like this, 4/3 H times R squared. Now, the pi H over 3 is just a constant with respect to R. So we'll get 2 pi H over 3 times R. Okay, and now that's dr. What about with respect to height? So let's rewrite it now so that we emphasize that pi R squared over 3 is a constant with respect to height. So that partial with respect to H is just going to be pi R squared over 3, okay, times dH. So this is our formula for the differential. Okay. Excuse me, sorry. So if we want to estimate the maximum error, then we need to take the worst case scenario, which is that the error in both directions, right, the error with respect to the radius and the height, are both 0.1 centimeters. Okay, so in the worst case scenario, let's use dr is equal to 0.1 and dh is equal to 0.1. Okay, and now keep in mind, because it could be plus or minus, so we could have minus and minus, we could have plus and plus. So we'll be able to tell at the end. We'll keep that in mind. Now, what should we use as our r? All of this is assuming that the radius is 10 and that the height is 25. So that's what we'll plug in for r. We'll plug in 10 for r and 25 for h. Okay, so 10 for r, so that should be 100. Okay, so what should we have? So we should have 2 times pi times 25 times 10 times 0.1 all over 3 plus pi times 100 times 0.1 all over 3. Okay, and then 10 times 0.1, that's just 1. So that should be 50 pi over 3. And then 100 times 0.1, that should be 10. So it should be plus 10 pi over 3. So we end up with 60 pi over 3, which is 20 pi. Okay, so that is the maximum, that's the maximum error. Now, just to get an idea, if we use 10 as our radius and 25 as our height, then we would get pi. So if we use, what's our formula? Pi r squared h over 3. And if we use 10 as our radius and 25 as our height, we would get 10 squared times 25 over 3. What would that be? That would be 2,500 over 3. Okay, 2,500 over 3. That's like 833.33. And a third pi. Now we'll say plus and minus 20 pi, right? Because it could be that you have an error of plus or minus 20 pi. The reason why I did the minus is, now if we go back and we use negative here and here, right? So if we use negative, then that's going to turn each of these values negative, so we would get negative 20 pi. Okay, so overall, you know, the 0.1 error, right, 0.1 centimeter error in just one of the dimensions propagated to, what is, let's see, what's 20 over 833? To like a 2.4% error in the entire volume. Okay. All right. The last thing we're going to do is we're going to briefly look at an example of working with differentials and linear approximations and increments with functions of 3 or more variables.